Unveiling the cosmos. The James Webb Space Telescope's groundbreaking discoveries. The James Webb Space Telescope, JWST, NASA's most advanced observatory to date, has transformed our understanding of the universe with a series of astonishing discoveries. Launched on December 25, 2021, with the ambitious goal of peering into the earliest moments of the cosmos, JWST has exceeded expectations, capturing breathtaking images and data that challenge long-held assumptions about the universe's origins and evolution. Among its most remarkable findings are the detection of the earliest known galaxy, a supermassive black hole exhibiting unprecedented behavior, and the vivid imagery of a galactic merger known as ARP-220. These discoveries, detailed in recent scientific publications and corroborated by other observatories like the Hubble Space Telescope, are reshaping our understanding of black holes, galaxy formation, and the Big Bang itself. This article delves into these findings, exploring their implications for cosmology and the future of space exploration, a new window into the early universe. The James Webb Space Telescope was designed to explore the universe's formative years, capturing light from stars and galaxies that formed shortly after the Big Bang, approximately 13.8 billion years ago. Equipped with a 6.5-meter primary mirror and advanced infrared instruments, JWST can observe objects too distant and faint for previous telescopes, including its predecessor, the Hubble Space Telescope. Its ability to measure extreme redshifts, shifts in light caused by the universe's expansion, allows astronomers to peer back to a time when the universe was just a few 100 million years old. This capability has led to discoveries that are both awe-inspiring and perplexing, challenging the scientific community to rethink fundamental theories about cosmic evolution. #, the earliest known galaxy. One of JWST's most significant achievements is the discovery of the earliest known galaxy, observed just 350 million years after the Big Bang. This galaxy, identified through spectral data from JWST's near-infrared spectrograph, NIRSpec, and near-infrared camera, NIRCam, is a testament to the telescope's unparalleled sensitivity. The light from this galaxy has traveled over 13.5 billion years to reach Earth, offering a glimpse into the universe's infancy. The discovery of such an ancient galaxy, along with 5 others of similar age, has stunned astronomers. These galaxies, some up to 10 times larger than the Milky Way, appear far more developed than theoretical models predicted for such an early epoch. The existence of these primordial galaxies raises profound questions about galaxy formation. According to conventional cosmological models, galaxies like the Milky Way take billions of years to form through the gradual accretion of gas, dust, and stars. Yet, JWST's observations suggest that massive, structured galaxies were already in place just 300 to 500 million years after Big Bang. Theoretical physicist Michio Kaku, commenting on these findings, noted that such discoveries challenge everything we thought we knew about the universe's beginnings. It takes billions of years to create a galaxy like the Milky Way, Kaku explained. So finding such large, young primordial galaxies is strange and may require us to rewrite textbooks on the beginning of the universe. #, a supermassive black hole defying expectations. In a discovery that has left astronomers in awe, JWST detected a supermassive black hole moving at an astonishing speed of 4 million miles per hour away from its host galaxy. This finding, reported in the Astrophysical Journal Letters by a team led by Yale astronomy professor Peter Bonda, defies the traditional understanding of black holes as gravitational behemoths that consume everything in their vicinity, including light. Instead, this black hole appears to be creating a trail of newborn stars stretching an extraordinary 200,000 light-years in its wake. Black holes are typically associated with destruction, pulling matter into their event horizons and emitting powerful radiation from their accretion disks. However, this black hole's behavior is unprecedented. As it moves through space, it interacts with surrounding gas clouds, triggering a cooling process that leads to the formation of new stars. The Hubble Space Telescope corroborated JWST's observations, confirming the presence of this star-forming trail. "We are seeing the wake behind the black hole," Bonda explained, highlighting the unexpected role of this cosmic phenomenon in fostering creation rather than destruction. This discovery has significant implications for our understanding of black hole dynamics and their role in galaxy evolution. Traditionally, supermassive black holes, which reside at the centers of most galaxies, are thought to regulate star formation by heating gas and preventing it from collapsing into stars. The observation of a black hole actively promoting star formation challenges these models and suggests that black holes may play a more complex role in shaping their host galaxies. Scientists are now exploring whether this behavior is an anomaly or indicative of a broader phenomenon that could reshape our understanding of cosmic evolution, the galactic merger of ARP-220. Another stunning discovery from JWST is the detailed observation of ARP-220, a galactic merger located 250 million light-years away in the constellation Serpens. Classified as an ultra-luminous infrared galaxy, ARP-220 shines with a brightness of 1 trillion suns, dwarfing the Milky Way's luminosity of approximately 10 billion suns. This cosmic spectacle, listed as object number 220 in the Atlas of Peculiar Galaxies, is a result of a collision between two spiral galaxies that began approximately 700 million years ago. The merger has triggered an explosive burst of star formation, creating a dense region spanning 5,000 light-years that contains about 200 massive star clusters. This region alone holds as much gas as the entire Milky Way, a remarkable concentration of material. Previous observations with radio telescopes identified around 100 supernova remnants within a 500 light-year area, underscoring the intense stellar activity in ARP-220. The Hubble Space Telescope revealed that the two merging galaxies are separated by just 1,200 light-years, each with a rotating ring of star formation that emits dazzling infrared light. JWST's infrared capabilities have provided an unprecedented view of this merger, capturing faint tidal tails, streams of stars and gas pulled outward by gravitational forces, and reddish-orange filaments of scattered organic material. These observations highlight the dynamic interplay between the merging galaxies, offering insights into the processes that drive galaxy evolution. The brightness of ARP-220 in the infrared spectrum makes it an ideal target for JWST, which excels at observing such wavelengths, revealing details invisible to other telescopes. Challenging the Big Bang Theory. The discoveries made by JWST are not only expanding our knowledge of the universe, but also challenging the foundations of modern cosmology, particularly the Big Bang Theory. The standard cosmological model posits that the universe began with rapid expansion 13.8 billion years ago, followed by the gradual formation of stars and galaxies. However, the presence of massive, well-developed galaxies just 300 to 500 million years after the Big Bang suggests that galaxy formation occurred much faster than previously thought. These findings raise questions about the cosmological inflation model, which describes a rapid expansion of the universe in its earliest moments. The model assumes that the early universe was relatively uniform, with galaxies forming slowly over billions of years. The discovery of large, complex galaxies so soon after the Big Bang suggests that our understanding of this process may be incomplete. Additionally, the absence of heavy elements like carbon in these primordial galaxies, as revealed by JWST spectral data, is surprising. Heavy elements are typically produced in the cores of stars and dispersed through supernova explosions, a process thought to take billions of years. The lack of such elements in these early galaxies challenges existing timelines of cosmic evolution. The Big Bang Theory itself faces scrutiny due to long-standing issues, such as its apparent violation of the laws of thermodynamics and the lack of a clear explanation for what triggered the initial explosion. JWST's discoveries amplify these concerns, as the existence of galaxies nearly as old as the Big Bang itself suggests that the universe's early history may be more complex than previously thought. NASA's recent announcement of a galaxy cluster observed just 650 million years after the Big Bang add another layer to this puzzle. This protocluster, expected to evolve into a massive structure like the Coma Cluster, indicates that galactic evolution was already accelerating in the early universe. The role of JWST's technology. The James Webb Space Telescope's ability to make these groundbreaking discoveries is rooted in its advanced technology. Its primary mirror, composed of 18 hexagonal segments coated in gold, captures faint infrared light from distant objects. The telescope's suite of instruments, including NIR-SPEC and NIR-CAM, allows it to analyze the composition, temperature, and motion of celestial objects with unprecedented precision. By observing in the infrared spectrum, JWST can penetrate cosmic dust clouds and detect light that has been stretched by the universe's expansion, making it ideal for studying the early universe. The telescope's ability to measure extreme redshifts is particularly crucial. Redshift occurs when light from distant objects is stretched to longer wavelengths as the universe expands, shifting it toward the infrared. By analyzing these redshifts, astronomers can determine the distance and age of celestial objects, effectively looking back in time. JWST's sensitivity to infrared light has enabled it to observe galaxies that were previously beyond the reach of Hubble, which primarily operates in visible and ultraviolet wavelengths. Implications for future research. The discoveries made by JWST are driving a new era of astronomical research. The observation of primordial galaxies, a star-forming black hole, and the ARP-220 merger has motivated NASA and other space agencies to develop even more powerful telescopes to further explore these phenomena. These future observatories will aim to confirm whether our understanding of the Big Bang and cosmic evolution aligns with the new data or requires significant revision. For now, JWST continues to collect data that could either validate or challenge existing cosmological models. The telescope's observations of galaxy clusters, such as a protocluster observed 650 million years after the Big Bang, provide valuable insights into the processes that govern galactic evolution. By measuring the velocities of galaxies within these clusters, astronomers can confirm their gravitational binding, offering clues about how massive structures form over time. The discovery of a supermassive black hole, creating stars rather than consuming them, opens new avenues for studying black hole interactions with their environments. Researchers are eager to determine whether this behavior is unique or indicative of a broader class of black holes that play a constructive role in galaxy formation. Similarly, the detailed imagery of ARP-220 provides a case study for understanding galactic mergers, which are critical to the growth and evolution of galaxies across cosmic time. Public engagement and the future of space exploration. The excitement surrounding JWST's discoveries has captured the imagination of scientists and the public alike. NASA has actively shared these findings through social media, including a recent tweet about the galaxy cluster observed 650 million years after the Big Bang. These efforts aim to engage a global audience, encouraging people to explore the wonders of the universe and support continued investment in space exploration. For those interested in staying updated on JWST's discoveries, subscribing to NASA's channels, liking and sharing their content, and enabling notifications are simple ways to stay informed. The telescope's findings are not only advancing scientific knowledge, but also inspiring a new generation of astronomers, engineers, and explorers. The James Webb Space Telescope has ushered in a new era of cosmic discovery, revealing the universe's earliest galaxies, a star-forming supermassive black hole, and the dynamic merger of ARP-220. These findings challenge our understanding of galaxy formation, black hole behavior, and the Big Bang itself, prompting scientists to reconsider long-held theories. As JWST continues to probe the depths of space, it promises to uncover more secrets about the universe's origins and evolution. Whether these discoveries confirm or upend existing models, they underscore the power of human curiosity and technological innovation in unraveling the mysteries of the cosmos. The answers to some of the universe's biggest questions may be closer than we think, and JWST is leading the way toward a deeper understanding of our place in the cosmos. Unveiling the cosmos, the James Webb Space Telescope's groundbreaking discoveries continued. The broader implications of JWST's findings and discoveries made by the James Webb Space Telescope, JWST, are not merely isolated breakthroughs, but part of a broader paradigm shift in our understanding of the universe. These findings touch on fundamental questions about the nature of cosmic evolution, the role of black holes in shaping galaxies, and the validity of the Big Bang theory. As astronomers continue to analyze JWST's data, the implications of these discoveries are becoming increasingly clear, prompting a reevaluation of cosmological models and inspiring new avenues of research. Revisiting the timeline of galaxy formation, the discovery of massive galaxies just 300 to 500 million years after the Big Bang challenges a conventional timeline of galaxy formation. According to the lambda cold dark matter, lambda CDM model, the universe's structure evolved hierarchically, with small clumps of matter gradually merging to form larger galaxies over billions of years. However, JWST's observations of large, well-developed galaxies in the early universe suggest that this process may have occurred much more rapidly than anticipated. These primordial galaxies, some of which are up to 10 times larger than the Milky Way, exhibit complex structures and significant stellar populations. This raises a question of how such galaxies could have formed so quickly in a universe that was still in its infancy. One possible explanation is that the early universe was more efficient at forming stars than previously thought, perhaps due to higher densities or different physical conditions. Alternatively, these galaxies may have formed through rapid mergers of smaller protogalaxies, a process